next we're going to take a look at what I promised you earlier today, finding the area under a curve, a region that we don't know the answer by means of a geometrical formula like a circle, like a triangle or a polygon. How can we find, for example, the area under a very simple curve, namely f of x equals x squared? And to make it as simple as possible, I'm going to say, let's say the area from 0 to 1. Now, of course, our goal ultimately will be to generalize this as much as possible. It could be any function, and it could be any interval. Can we find the area under that? But we're going to start with a very, very simple example, which is this one, x squared from 0 to 1. By the way, if x is 1, what is y at that point? Y is 1 as well. Let me ask you guys a question. Give me a very rough estimate. And when I say very rough, I mean very rough. You know, like, you don't have to be specific. You don't know the tools, of course, yet. And if you've seen calculus, please refrain from answering the next few questions. But can you give me an estimate as to what this area under this curve might be? This area here. What might it be? Somebody said 0.5. It's a good estimate because what is the area of that square? Because it's 1 by 1, right? This entire square would have been 1 unit, right? This is clearly less than 1 square unit, right? And if you think about this triangle here, what is the area of this triangle on the lower half? It's 1 by 1. So area of a triangle is base times height over what? 2, right? So it's 1/2. So it looks like the area that we're looking for, that the one that is covered in blue lines, is going to be less than what? Less than 1/2. So we already have a pretty good idea. We've already eliminated choices a little bit. So it has to be anything greater than 0, obviously, and less than 1/2. It's a number in that range. Now we're going to try to make even a better refined estimate. And it turns out that, you know, one of the easiest geometrical figures to work with is a rectangle. So we're going to try to see, in a sense, how many rectangles we can fit in that little area. One way you can do this is, for example, you could go ahead and split it 1/2. Okay? You could go to the function, get a height there, and from there you get one rectangle. I'm going to do this in a little bit in more detail. Right now, if you like, just try to kind of follow what I'm doing. In a little bit, I'm going to do it more rigorously, and I'm going to give you like detailed notes. But right now, say I want only 2 rectangles. So, and to get the heights, I go from here to the function. I get the heights. So I do a second rectangle. You know, this is going to be obviously an overestimate, right? But what would be a better way to estimate it? So if I could find the area of those 2 rectangles, that's going to be a very, very crude estimate for the area under this curve. Obviously, you have a lot of overflows there, right? What could be a little bit better refined estimate for us? Instead of using 2 rectangles, like what could I do? Think of it this way. Think of the same function here. Okay, let's say that I superimpose it on some grid paper. Okay, say you have a grid paper here. Here, instead of rectangles, we're using squares, right? How could you estimate the area under the curve there? You could try to add up all the little rectangles, right? And if there's a little, you know, put like 3 of them together, you know, if they're not making a whole rectangle. But my question to you is, if you want to make a really good estimate for the area under that curve, and if you have your choice of grid papers, say large grid, small grid, very fine grid, what would your ideal grid paper look like? The one with the large grids or the one with the smallest possible grid? Smallest possible, because the large grids are going to have bigger overflows. Like I had here, a very big overflow, right? Whereas a very small grid, if I could have this like very, very small grid paper, then everything is going to fit in there even better. But usually in mathematics, instead of working with these tiny little squares, we work with rectangles. And I want to do a quick demonstration to you about what happens if you increase the number of rectangles. Do you really have a better estimate for the area under that curve? Let's see. So I'm going to use the right-hand side to get my heights. Right now, they have an interesting function here. The function is written up there, x plus 0.1x squared minus 3 sine x. So it's a funny-looking graph there. Right now, they have only, it seems like, I see only one rectangle. Let's see. Okay, I want to plot the right-hand rule. Okay, I want to increase the number of partitions. Let me increase it to, if I can, to 4. I'm going to start with 2 and double it. So double the number of partitions. Now they have 2 rectangles to represent the area under that curve. Now they have 8. I keep doubling it, okay? If I double it again, now they're using 16 partition points. You see the overflows, still overflows. Some places underflows, like these 3 rectangles are not really fitting that well in that curve, right? And I'm going to increase it still more, double it again. You see the overflows, underflows are getting smaller, double it again. Right now we have 64. You see how tiny those overflows are right now? We're really fitting those rectangles pretty well in that space. I'm going to double it one more time. After a point, you can't even see the difference between the rectangles and the area under the curve, right? In other words, what we're doing here is really amazing. We're using something we already know. We know how to find the area under a rectangle, right? The rectangles are really easy, length times width. So if we can fit a lot of rectangles under that curve and add those up, then we're going to find the area under the curve. And in the ideal case, think you could have anything you want. In the ideal case, how many rectangles would you really want to have under that curve? Right now, I have 256. I'm going to keep doubling it. Right now, I have 512. After a point, you won't even see a difference. But ideally, how many do you really wish to have under a rectangle to have a perfect coverage with no gaps, no overflows? Infinity, right? If we could have anything we wanted, we would want to have infinitely many rectangles. That would be the perfect area. So we could take a limit as the number of rectangles go to infinity. That will give us the perfect coverage. Okay, so let's keep that in mind. But we're going to now come back and let's see. So back to our basic example. F of x equals x squared. Okay, so what I'm going to do to begin with this example is I'm going to split it into 4 rectangles because we've got to go slow. Yes, we want, if possible, infinitely many rectangles under that curve. But to get there, we've got to start in small increments. So first, to show you how I can go from, from a finite many rectangles to infinitely many rectangles, I picked a simple example. I have 4 rectangles, as you see here. And I'm using a notation here. You see I say capital A, 4, comma, R. You know what that means? I'm going to find the area under this curve by using 4 rectangles. And does anybody know what that R means? You might think it represents a rectangle, but in this case it represents right-hand side points. I'm going to use the right-hand side point. For example, if I take the interval from 0 to 1, and it's split into 4 sub-intervals, 1 at 1/4, 1 at 2/4, 3/4, and 4/4. Now take the right end point of each of these partition points, go to the function, that gives you a rectangle, right? Take the right end point, go to the function, gives you another rectangle. Same thing, take the 3/4, go to the function, get a height, create a rectangle, and the last one do the same. Go to the function, get a height, and create your rectangle. So my question will be right now, what is the sum of the areas of these 4 rectangles? And our job is going to be searching for patterns. Like we're going to go from 4 to 10 to 20 to 30. We're going to try to see a pattern and see if we can actually go to infinity from there. See if we can extend our pattern to find the exact area under this curve. So right now we're just concentrating on 4 rectangles and using the right endpoints. Who can tell me the area of that very first rectangle there? This guy right here. What is the area of that very first rectangle? Again, rectangles are easy, right? Base times height. What is the base of that rectangle? Actually, every one of them has a base of 1/4, right? And what about the height of that rectangle? Remember, this function is f of x equals x squared function. So you plugged in 1/4 into the function to get the height. So what do you think the height will be there? 1/16. In other words, you plug in the right endpoint into the function. So I'm going to square it. If this had been the cubing function, you would plug in the 1/4, that right-hand point, into the cubing function. But here we have the squaring function. That's how we got that height, by plugging 1/4 into the function. What I have up there is the area of the first rectangle. Now I want you guys to help me with the next. Okay, let me have somebody from the first row, please, to try to help me write down what's the area of the second rectangle. First of all, what is the base of the second rectangle? Again, originally I had a distance of 1 unit. I divide into 4 equal parts, so each one of them is going to have a base of 1/4. So the base of that one is still 1/4, right? And what about the height of the second rectangle? You simplify. You said 1/2 squared. I'm going to keep the pattern. I'm going to keep it like 2/4 squared. Same thing, really, right? But I'm just going to, so the base is 1/4, and the height is, take the point 2/4, plug in into the function to get the height, so you have the squared. Okay, could someone from this row, please, from the middle row, help me out the next rectangle? What will be the area of the next one? What is the base? Okay, so just to be clear, I would like somebody from this row, please, to give me a possible answer. Right, the base is 1/4. And what about the height? Right, now we're plugging this into the function, so it's 3/4 squared, right? And the last one, the base is, let me have somebody from the row, from the last two rows, since there are not enough students on the one before last. So the base would be 1/4. And the height would be, it's really 1, but I'm going to keep the pattern. I'm going to put like 4/4, because we had like 1/4, 2/4, 3/4. So let me put it 4/4, take that right endpoint and plug it into the function squared. So if I get this, I'm going to have an estimate. Do you think this estimate is more than the correct area or less than the correct area? More than, because we see the overflows occurring there, right? So let's go ahead and calculate this. I'm also going to write this in summation notation, so you can also see how it can be done with the sigma notation. This is the summation. There are 4 things we're adding, right? So I from 1 to 4. Okay. What is the only thing that is changing? Okay, I'm going to wait because some of you are calculating this, so let me wait for a minute. So some of you are entering this into the calculator and you're going to get a single number. Please hold that thought. I'm going to ask that from you in just a little bit. Yes, Ryan?
4, R.
Yes. 4 represents 4 rectangles, and R is the right-hand points. Like if you look down here, I have 4, L. I'm going to use 4 rectangles, but I'm going to use the left endpoints there. Basically, you can use the right endpoint to get the height. You can use the left endpoint. To be honest with you, you could use the midpoint. You could use any point in that interval, as it turns out. But right endpoints usually make it the easiest one, so I'm starting with that one.
So we're finding 24 to a rectangle.
For example, on the first one, what was the base? 1/4. And what was the height? But what is the height? This is the x squared function, right? The height was obtained by plugging 1/4 into the x squared function. So that's how we got the height of the first rectangle. And if you multiply base times height, you're getting the area of that first one. Okay, and do the same thing now for the second one. 1/4 is the base, exactly. And the height was obtained by plugging 2/4 into the function, right? So there we got that one. So we have a sum of 4 things because we're adding 4 areas, basically. And my question right now to you is, in a sense, sort of the opposite of what we've been doing. Earlier, I gave you a sum, you expanded it, right? Now you have an expanded form. I'm asking you, can you give me this as a sigma notation in compact form? So I'm trying to write this. The summation I goes from 1 to 4, because we're adding 4 things, right? What is the only thing that's changing as you go from the first term to the second to the next? What's the only thing changing? The numerator under the parentheses, right? So that's your variable, that's your I. Okay, so everything else stays exactly the same because those are not changing. So this is how we can write it. 1/4 times, you tell me, what should I write under the parentheses? My variable is I over 4 to the power of 2. As I goes from 1 to 4. Let's check this out. Okay, does it really work? Let's check it out. If I is 1, you get the first one, right? If I is 2, you get the next one, etc. So this really works. Now for this question, you really didn't need anything fancy like this because you can easily calculate this on your calculator, but remember, we're trying to do the impossible. We're going to try to do infinitely many rectangles here. To get to that, it would help to be able to have a compact notation because after a point, writing even 10 of these next to each other is very tedious. The summation is really going to help us in just a little bit. Okay, so what did you guys get as the answer for this? Pardon me? 15 over 32? 0.47. That's a little bit better than the last estimate we had, is it not? Because remember last time we said 0.5, it was less than 0.5 because we took the triangle, right? So now we have made a little bit progress there, right? We said area should be less than, let me write that down here. The area should be less than 0.47. Now we're going to take the left endpoints. This is going to be a lower estimate, obviously. So 4 rectangles. This time, take the left endpoint to get the height. Like the first one turns out to be just a 0 height, nothing there. Second one, take the left endpoint to get your height, to get this rectangle. Then take 2/4 to get your height, you get this rectangle. And take the 3/4 to get your height, you get this rectangle. Now I want to add the areas of these, technically 4 rectangles, but the first one turned out to be just 0. So the base was 1/4, but the height was 0 for the first one. Okay, who can tell me the area of my second rectangle here? So right now I'm using the left end points to get the heights. This is going to, the base is 1/4, correct? We're plugging in 1/4 now into the function, so it's going to be 1/4 squared. The next one, base is 1/4. What about the height? Now we plug this point into the function to get the height there, right? So 2/4 squared. And somebody other than Ryan, please, to tell me the last one, which I'm glad that he's able to get them, but I want to see everybody's getting them. So how do you find the area of the last one? The base is 1/4, and the height is, say it again, please? 3/4 squared, because now you took the left endpoint to get your height. So that will be times, as Daniel suggested, 3/4 squared. Okay, could somebody quickly put these into the calculator? The first one is 0 anyway. Let's see what we're getting here. And we know the correct area has to be greater than this, right? Because there are underflows here. There's a lot of gaps that these 3 rectangles could not cover, right? So what we get here is going to be an estimate that is below the correct answer for the area under the curve. So let's see what we're getting here. I have something that starts with a 0.2. Let me know if you have the rest. Okay, I heard 7 over 32. 0.219 roughly. So let's say roughly 0.22. So we're saying the area is going to be greater than 0.22. But it's going to be less than 0.47. This is the best estimate that we have right now. Again, we're getting closer. We want to refine it even more if we could. It could be 0.3, it could be 0.35, but there are still infinitely many answers in that little interval there. So this is a good start, but we're not there yet, okay? But you'll be amazed. In the next 10 minutes, we're going to be able to do 500 rectangles because our calculator has a command called sum of a sequence, and I'm going to show you how to do that. So we're going to be able to, in just a few moments, we're going to be able to fill out the following 2 tables, and I'm going to give you some time. I'm going to explain to you what to do. The right sums and the left sums. We already have the answer for 4 rectangles, right? In a little, we're going to do 10, 50, 100, and 500 rectangles. Same thing for the left sums. But before I get there, Daniel, I think you had a question.
I didn't get that 0.
0 because I'm using the left endpoints to get my heights. So what is the left? So if you take that first interval from 0 to 1/4, the left side of that interval is 0, right? Plug 0 into the x squared function, the height will be 0.
How can you do that for the top of it?
Because there we're using the right endpoints to get the heights. So there we plug in 1/4, 2/4, 3/4, and 4/4, right? Here we're using the left endpoints to get the height. So we plug in 0, 1/4, 2/4, and 3/4 into the function.
So then you don't use 1 then?
We don't use 1 in this case, right? We got the height from the 3/4. This is called the left Riemann sum, and the other one is called the right Riemann sum. What I'd like to also write here is, can you tell me this one? How would you write this one as a summation notation? And again, there's 4 things that we're adding. Would you agree with the following? I'm going to write this one down. Would you agree with this one? If I is 0, you get the first term, right? If I is 1, you get the next one. If I is 2, the next one. If I is 3, you get the last one. What was the major difference between this and the previous summation? Where the I started. Basically, for the right sum, you will always have I from 1 to n. For the left sum, you will have I from 0 to n minus 1. That's going to be the only difference between a right sum and a left sum. So right sum starts from 1, it goes all the way to n. Left one starts with 0, goes all the way to n minus 1. Okay, we're getting ready to fill in this table in, but I got to show you something about calculators, because otherwise imagine adding 500 numbers to each other, one at a time. That would be a nightmare, right? But luckily there is this great command in your calculators. As a matter of fact, let's use it to check this answer right here. Let's use the command to check this answer. This one, we got 0.219, right? Here's how you can enter this into your calculator. This summation, you can enter it like the following. You can say sum of a sequence. That's what summation is for TI-83. Sum of a sequence. This 1/4, you could, if you want, you can factor it outside, or if you want, keep it inside. It won't matter that much. I'm going to show you the commands in a little bit. At the moment, let's just write it out, okay? So sum of a sequence. That 1/4, I'm going to go ahead and factor it outside, 1/4. I over 4 squared, this is how I'm going to put it, x over 4 squared. And then it wants to know comma the variable x, and from where to where you're going. Like in this case, we're going from 0 to 3. Close it for the sequence, close it for the sum command. Now let me show you how you can enter this on the calculator. The sum command, I believe, is under second stat. Second stat opens the list menu. Let me get my calculator going. So go to second stat and go to math. Math under that. You will see the sum command right in there. So second stat. Okay, go to math. There's your sum command, number 5. Okay, where are we going to find the sequence command? Again, go back, second stat. Second stat. Go under operations. Sequence is number 5 in there. So I went to second stat, which opens the list menu. Under math, I had sum. Under ops, I had sequence. Okay, what am I going to put right now? In parentheses, I over 4 squared, but I'm going to put x over 4 squared, comma the variable, comma, from where to where? For the left sum, we're going from 0 to 3, I believe. 0 to 3. And I didn't put my 1/4 outside of everything, but later I can divide this answer by 4. So first I do this, and then divide by 4. Same answer as we got earlier, right? Okay, let me go around, see if anybody's having trouble finding these keys on the calculator. Any questions? Good question. Comma is right above number 7. Comma is right above number 7. Yes, if anybody's looking for the comma, it's right above number 7. Any other commands you're looking for? Okay, just to show me you really understood this, can you also check the right sum? For the right sum, do a second enter to reproduce the command from the top. Second enter again. Okay, sum of a sequence. From where to where are you going to go on that one? From 1 to 4. From 1 to 4. And the second enter is very convenient because when you do like 4 rectangles, 20, 30, 500, if you do second enter, you can reproduce your command very easily. Okay, just press enter and then divide this by 4. Did we get it? We did, right? So this command works very efficiently, and it's going to be a lifesaver when we have something like 500 rectangles that we're adding together. Okay, so going back to, oops, what happened there? Okay, so going back to this table that I will ask you to fill out, I've already done the answers for number 4. If you're using 4 rectangles, what was the right sum? The right sum was 0.47, right? What was the left sum? 0.22. As you increase the number of rectangles, there's going to be less and less overflows and underflows. And we're going to have a really good estimate here between the upper sum and the lower sum. And we're going to have a really good idea what this actual area is. Now, let me just help you set up number 10 rectangles. Let's go ahead and set up what happens with 10 rectangles. Okay, how would you set it up for 10 rectangles? Say the right sum. Okay, first, don't worry about the calculator command, but the base is going to be 1 over 10 for each one, right? And the height is going to be something like 1 over 10 squared. If you like, let me factor this base outside. So each one has a base of 1/10, and the height is 1 over 10 squared, 2 over 10 squared, all the way to 10 over 10 squared, right? How would you enter this into the calculator? 1 over 10 times what? Sum of a sequence. Tell me again, what goes in here? X over 10 quantity square, comma x, comma, from where to where for x? We're doing the right one right now, the right sum. From 1 to 10. And if you're going to do the left one, what would be the only difference? You will go from 0 to 9, correct? So you do a lot of these second enter features. To save a little bit of time in class, I'm going to ask everyone do the case n equals 10. Okay, after that, these two groups, could you please just do 50? Please do what happens in 100 rectangles. And please do what happens for 500 rectangles, and I'll take your answers in just a moment, okay? Stop the recording here. For n equals 10, what do we get for the right-hand side? Endpoints? 0.385 or something like that, 0.39, correct? Mm-hmm. Did everybody get 0.385 for the right sums? Okay, what about the left sums? Okay, roughly 0.285 or 0.29. Okay. The right sum's 50. Did anybody get that far? The right sum's 50. I think you two, we're going to work on that. 0.34, etc. 0.34. And the left sum with 50? Good. Excellent, Daryl. Did anybody get to 100 for the right sum? Yes, Christine? 0.338. And the left sum? 0.328, 328, something like that. Okay. Anybody did 500? Yes, Hazel on the back. For the right sum, you got 0.334. And for the left sum, 0.332. It's becoming pretty obvious now where this is going to end up. Do you see a pattern there? You know, like the left sums and the right sums are all converging around 0.33 something, right? And remember, the right sums were the overflows. Hold on, I think I put them backwards for the, I'm sorry, the last one you said the right sum was 0.334. That should be over here, 0.334. And the left sum should be 0.332. 0.332. Okay, so the right sums are the upper limit. So basically, the correct area should be less than that amount, right? Because you see, the right sums had these extra spaces. So that's an overestimate. And the left sum is an underestimate. The left sum was 0.332. So we have a pretty good idea about what this is going to be, right? What do you think the area under that curve is roughly equal to? Maybe 0.33. If we take a really rough, wild guess, there's a fraction. What might you say? Maybe it's exactly 1/3, right? So this is a pretty good idea we have. It should be really close to 0.333, right? Between 0.332 and 0.334. We're guessing it's going to be exactly 1/3. Now, what we just did was a numerical estimation. It's pretty good, but it's very time-consuming. And also, you know, mathematicians would say, well, you know, you cannot rely on calculators so much. You've got to do things by hand analytically. So now we're going to move on to the analytic side and try to get the same answer doing analytically. And then another problem with this is we have 500 rectangles, which is really good. But infinite rectangles would be better, right? So you can do infinity if you are taking, you know, limits, if you do analytically. So that's what we're going to do next. We're going to do this with analytic means. Pardon me? Right. Basically, the correct area should be between this number and this number. That's what I wrote here. That's what we're guessing right now. Exactly. And also look at this. You know, there's a limit. These numbers are approaching to 0.333. These are approaching to 0.333. So everything is leading in that direction, basically. Now we're going to try to do this analytically. Okay, let me cover this up. Go one step at a time. Okay, now we're going to try to find the exact area. Okay, to find the exact area, I'm only going to worry about the right-hand sums because just to make it less cumbersome. So I don't have 10, I don't have 100, I don't have 500, but right now I'm using n rectangles. So do you see what happened here? Instead of saying like, if I had 10 rectangles, I would say 1/10, and I would have summation of like I/10 squared. But instead of 10, I'm taking n rectangles right now. So what is the base of each of my rectangles? So if this whole interval is unit 1 unit, and you want to have n rectangles, so each one is going to be of base 1 over n. And the endpoints are going to be 0, 1 over n, 2 over n, all the way to n over n. So what does this represent, this one right here? This is the base of each of the rectangles, right? The base is 1 over n, each one, right? That's why I factored it outside. And what is the height of each rectangle? Like plug 1 over n in there, you get a height. But plug 2 over n in there, you get a height, right? If this is your x squared function, so you get the height by plugging I over n into the x squared function. So you have like 1 over n squared, 2 over n squared, all the way to n over n squared. So for this example, we're not using a specific number like 5 or 10 rectangles. We're using a general, which is n rectangles. Okay, now we need to simplify this. Okay, how can I simplify this? Square that quantity under the parentheses. Square it, and this is what you get. I squared over n squared. Now, tell me, what is the real variable here? Is it I or is it n? Which one do you think is the real variable? I. The index of the summation tells you what is changing, what the variable is. I is the variable. So what can you take outside of the summation notation? You can take out the 1 over n squared. The I is the variable that has to stay in. Okay, so take out 1 over n squared. So what are we going to be left with? 1 over n times 1 over n squared inside the summation of I squared. Remember, we're doing this for n number of rectangles. Now, can you tell me a formula for this? What do we know about this? We just learned that today. And the first two is 1 over n cubed. And Ryan is correct. Summation I squared we learned today is n times n plus 1 times 2n plus 1 all over 6, right? So here we have area using n rectangles and using the right sums. But how many rectangles do I really want to have the exact area? Infinitely many. So we're going to do a very ambitious thing here. We're going to say the exact area A equals, it's the limits as n goes to infinity of the above. So let's take a limit of the above. Take the limit as n goes to infinity of not going to do it. Okay, so when I rewrite the above, I'm going to rewrite it in a more creative way. If you have n times n plus 1 times 2n plus 1, tell me the highest degree term there. If you were to multiply n times 2n, what would that give you? It would give you 2n cubed, right? Plus, you'll have all sorts of other things. But the highest degree term of the top is going to be 2n cubed. Right? What about on the bottom? We have 6n cubed. Something we learned earlier in this class. How do you take the limit as n goes to infinity if the degree of the top is equal to the degree of the bottom? Take the ratio of the leading coefficients. In this case, exactly 2 over 6. Does that sound familiar? So 2 over 6, last time I checked, it also can be written as 1/3. And wasn't this what we were guessing the answer was going to be very close to 1/3, right? We even made the guess about saying maybe it's exactly 1/3. When you do infinitely many rectangles, you take a limit. In that case, we get exactly 1/3. Yes, questions?
How'd you get the 1 over n cubed? Like, where did the extra 1 over n and 1 over n squared come from?
Okay, give me one second.